Okay, we're in section 130. There'll be contents to read through. It's a tough read. There's examples to look at and exercises to do. My name is Ron Bannon. This is a draft version of my adaptation of Webster Wells' Advanced Course in Algebra, which dates back to 1904. This PDF that you're looking at now was being made available to the participants in the Prison Mathematics Project. I realize there may be people out there, both teachers and students, interested in getting a copy of this document. It's not published yet, but it will be published. If you want to inquire more about that, reach out to me. My name is Bannon. My email address is also Bannon. That's B as in boy, the @ symbol, NNON.US. All right? So let's take a look. And it's going to be a tough read. All right? So first off, about constructing a graph, which I think is important. We'll talk about that as I go through the problems. I do want to point out there's a difference between the way I graph and the way Webster Wells graphs. If you notice, that's the same curve, by the way. It looks really different, though, doesn't it? But it's really the same type of look. I would claim that this is more like a pre-calc sketch, all right? This one over here is a more detailed calculus-type sketch. We see a lot of features in the curve that you're not seeing in Webster's. They do a good job, though, I'll say that. This machine does this one over here, though. So this is a tough section. This is particularly difficult, all right? But anyway, I would read through that, try to make sense out of it, all right? It's not easy to do, though. And then they go through some examples, yada, yada, yada. It's a lot of work, all right? So what I do, let me get to that and get to the examples. I'm scrolling through that pretty quickly, right? Yeah, it takes time to read through that. They also mention about continuity, all right? That's an important topic. So I have a little different take on what he's doing. And by the way, he is using derivatives. I'm going to use derivatives slightly different than him. But here's the deal. I mean, I would look at all kinds of alternatives. The more tools you have at your disposal, the better. All right? My claim over here is I think you should look through this stuff as well. All right? I think you should look through this. Of course, I'm going to be looking through it. As I do the problems, the way I'm going to do them, and again, I write this up for you. I certainly use the method that he's describing. I like his method. I believe it's a little mechanical. It's still being taught, by the way. If you go to the web, you'll see, plenty of papers on this, how to do that. But what I want to do is I'm going to take a slightly different approach to the problem. And the way I'm going to do this one over here is I know it's a cubic, and they want to determine the nature of the real roots of the problem over here. So, like, for example, I know this cubic over here, it looks sort of like this over here. What I don't know is looking at it, just a cursory look at it, I know it has at least one root. For example, let's say the x-axis is here. I know it has at least one root. But the deal is about that the x-axis could be right over here. It might have 3 roots, all right? It could also have 2 roots, something like this over here, all right? So I'm going to say I'm not really sure. So what I'm going to do is I'm going to erase this over here. I got a general shape of it. But I don't know, maybe it has 1 root, maybe it has 3 roots, maybe it has 2 roots, all right? So let me go through that again. Different color. Maybe the x-axis is here, 1 root. Maybe the x-axis is here. That would be 1, 2, 3 roots. Maybe it's here. That would be 2 roots. Again, I'm pointing out the roots here by just circling them. And again, I'm showing him what the hypothetical x-axis. The x-axis could be there. All right? Now, again, I'm going to erase this. Again, it's in a lot of erasures, but it's easy to erase. But really I'm going to boil this down to, whoops, sorry about that. I'm going to boil this down to, get my eraser out again. I'm going to boil it down to an analysis problem where I'm analyzing something. I'm analyzing a cubic that I know looks like this over here. And what I'm going to do is I'm going to talk about these points over here. And these are what's called the relative extrema. This is a relative minimum here. This is a relative maximum over here. All right, the way I'm going to do that, put derivatives down. And I'll go through that with you. Now, before I do anything, I want to claim that I got a really easy point in this problem, and that's the y-intercept of 1. All right? I got that. But what I don't have is I don't know the general I know the general shape. I just don't know where this thing has this relative min, relative maximums. So I want to put that down for you. All right, so I'll put derivatives down for you. So f prime of x equals 3x squared minus 4x minus 1. Again, you may have to read over the introduction stuff that I'm talking about for these extrema, but I got to, basically look at what they're talking about here. And I'm going to put this down for you. So let me write this over here for you. And I can't factor it, but I would like to know when it's 0. And I'm going to do that now for you. I'm going to say x equals, a little tough here, isn't it? I got to do twice the a on the bottom, that's 6. Minus the b, that's 4. Plus or minus, right, square root. I'll clean this up later. Let's see, b squared, that's 16. Minus 4 times a times c, that's going to be plus 12, right? Okay, let's keep going. X equals 4 plus or minus, well, that's going to be root 28, right? Over 6. So let me get my eraser out. Erase this over here. And I'm going to put this down for you. And as I do this, I know this is tough, but I'll put this derivative down. And I know I got 2 zeros. And my first 0, for the derivative, by the way, is going to be 4 minus root 28 over 6. And the other one's going to be 4 plus root 28 over 6. All right? All right, let's take a look. Well, it's easy for me to analyze the derivative between these two numbers by just doing simple sign analysis. So if you chose 0, what would you get? You get negative, which means the curve is going down, as expected, by the way. Now, if you took a number after 4 plus root 28, well, I'm going to play it safe by taking a number like, 10. And what would you get? Positive. So I know a minimum occurs here. This is where a minimum occurs, min. All right, a minimum occurs over there. All right? And let's do it to the left of, 4 minus root 28 over 6. I'll say minus 10. You plugged it in. It's still positive. So this is where you're plugging it into the derivative. So now I know I got a maximum. So I'm pretty clear about this over here, that this is going up here, and there's going to be a maximum over here. Again, I'm not sure exactly where that point is, but something like this over here. All right? All right, I know there's a root over there. Now, I'm kind of wondering about, where this minimum, maybe it goes something like this. And certainly I don't want to do too much, arithmetic here, but I'm going to search around, right? Because I don't want to do much arithmetic over here. And what I want to do is I want to use the intermediate value theorem. And for example, I know f of 0 is positive. Let's try f of, let me take a look. So we're going to do integers, right? So the integer I want to do next is what? I guess I would try, well, if I do 0, what would the next integer be? Probably 1, right? This might seem crude to you, but if I did f of 1, and again, we're plugging it in over here, I would get 1 minus 2. That's minus 1 minus, oh, it's negative. So I'm going to say at 1, it definitely has to puncture here. Now, again, I'm not sure when it goes back up again, but I know the general shape of it. So I'm going to do, let's see, I did 1, right? I know it's negative. Let me do f of 2. And what's going to happen there? Well, you get 8 minus 8, that's 0, minus 2 plus 1. That's still negative, isn't it? So I know at 2, it's still negative. But again, I'm not sure, how low it goes here. You know, I don't know about that, but I know it's still negative over here somewhere. Let me go to f of 3. And what would you get there? 27. That's not so bad. And then what do you get? Let's see. 27 minus 18. It's definitely positive, right? So when you get over to 3, the thing is up here somewhere. So I'm going to see you're seeing something like this over here. So I'm seeing my roots over here, all right? Now, by the way, I want to talk about this one, and this is a very crude picture, but I'm not saying it's a good picture. So I'm going to do the other, I'm still using the intermediate value theorem. Let me get my eraser out because I want to go backwards on this. Sorry about that. F of 0 was positive, right? And what's f of minus 1? Let's take a look at that. And again, we're doing the function. Let's see, minus. I got to do that. Let me make sure I'm doing that right. So minus 1, you'd get minus 1, minus 2, plus 1, plus 2. Oh, it's negative. All right? So I know that the root, and this is minus 1 over here. Okay, so I know where the roots are now. So the roots are on the intervals between minus 1 and 0. Another one occurs between 0 and 1. And the other one occurs between between 2 and 3. All right? Again, I want to point out where I'm seeing that stuff. Here, here, and here. It's a very crude picture. By the way, I also know where the extrema occur, but these are kind of nasty looking numbers, and they're not asking about that anyway. But I know those extrema are occurring over here. I know that. So what are the natures of the roots? We got 3 real roots, and we know approximately they are. You know, the first root I'm seeing is between, whoops, I made a mistake in the notation over there. Minus 1 and 0. I know that. We did the intermediate value theorem for that. And the other one's between 0 and 1. We used the intermediate value theorem to do that. The other between 2 and 3. We got the general shape of it. Now, granted, I do want to point out you should be looking at what Wells is doing as well. All right? Use Sturm's theorem and look through that. All right? I write it up for you too. Write up the way I would have it written up. It certainly looks a little bit different than what Wells does, but the bottom line, it's not bad. All right? Now, I also want to point out that, I talked about the intermediate value theorem. I like that. This is the general shape of the curve over here. And I'll put this down for you. And before I told you the root between minus 1 and 0, another root between 0 and 1, and the last root I found between 2 and 3. I also said there was extrema here, all right, relative mins, relative maximums, and although they're not asking for it, they're pretty easy to determine where they are. All right, let me do the next one. Well, I think it's going to be a little bit easier to do. I'm going to do the same type of analysis, all right? So what am I going to do? Let's write this down. And again, I got a general idea that this thing is shaped like this over here. General idea. But my problem is this. I don't know where the x-axis is. Could be there, could be here, could be here, could be here, right? If it's the first one, that's 1 root. If it's there, it looks like 2 roots. If it's here, it looks like 3 roots, 1 root. So again, yeah, I know there's at least 1 real root. That's about all I know at this point. So let me erase this over here, and I want to go through that derivative business again, all right? And again, you realize a little bit different what Wells is doing. I'll write the derivatives down for you, though. They're pretty easy to write down. This is the function. That's the first derivative. That's the second derivative. And someone says, why do you do the second derivative? The second derivative kind of tells me, it reinforces my belief about where the extrema are. And why is that? If you read back over what we were saying over here, this guy over here, whoops, sorry about that. This guy over here, it's the 0 occurs at x equals 0. So what do I know? I know looking at it, to the right of 0 is positive, and to the left of 0 it's negative. So I know there's going to be like a min on this side over here, and I know there's going to be a max over here. All right, I know that much from that second derivative. Let me kind of erase that information because, I kind of knew that anyway. What I mean by that, I knew the general shape. What did I know? I know it looked like this guy over here, where there'd be a max and a min. That's not a surprise to me. And what do I know? It's occurring on the below the 0 and then above the 0. So, maybe I should do a little graph of that, all right? And let me get my eraser out. And I know, I'll put this down over here. I'll put the y-axis down. That's about all I can do at this point. I know there's going to be an intercept at minus 5. I'll put this over here, 0, minus 5. And by the way, I know it looks, I'm not really quite sure, but maybe something like this over here. Now, I hope you realize, at the very minimum, to the right of 0, I definitely have one real root. But I'm kind of wondering before that, what happens before that. I mean, the x-axis, and I'll put it down what I mean by that, it could be here, right? It could be up here. I'm not sure where it is, all right? So what I'm going to do is I'm going to try to find that maximal point, right? That's going to be over here somewhere, right? I'm going to see if I can figure that out, right? I don't know if I can, but let's see if we can do it. Well, I think I can, because I'm looking at that first derivative, and I notice this over here. You could factor it. 6 comes out, and what do you get? 2x squared minus 1. And that looks pretty easy to do. I'll write down here that that's got a 0 at, let's see, that would be, let's see, that's pretty simple, isn't it? That's plus or minus, let's see, minus 1 over root 2, and the other one's going to be 1 over root 2. All right? Now, certainly, you just simple sign analysis on that. This is the first derivative, I mean. At 0, it's negative, going down. 1 over root 2 after that, if you choose, like, I don't know, 100, it's positive. Well, this makes sense. I'm getting a minimum here, and that would occur at 1 over root 2. All right? I don't need to compute it, by the way. I certainly know it's negative. Right? It has to be below the minus 5. I know that much. Let's do the minus 1 over root 2, though. And I'll take a number below, like minus 100, plug it in. You still get positive. So I know there's a maximum here, a max. So a local max occurs at minus 1 over root 2. Now, I'm going to do a quick evaluation of that. And my concern about this is not the actual number. I'm wondering, is it a positive number or a negative number? So I'm going to put this down, f of minus 1 over root 2. And what would you get there? 4 times minus 1, 2 root 2's. I'll write that down. Then what do you get? Plus 6 over root 2 minus 5. All right, I got to keep doing that. And this was a lot of work, isn't it? So what do you get? You get minus 2 over root 2. I think I did okay there, right? Plus root 6. I'm sorry, plus 6 over root 2. I'm sorry, I misspoke. Minus 5. Well, again, I'm just trying to figure out, is that a negative number or a positive number? And what do you get? You get 4 over root 2 minus 5. Well, I'll be honest with you, looking at it, I think it's pretty easy, but you may disagree with it. 4 divided by root 2 is definitely less than 5. All right, it's definitely less than 5. So if it's less than 5 minus 5, this is a negative number. So what do I know now? I know that this point over here is below the x-axis. Whoops. What did I just do there? I guess I flipped it. Let me see if I must have undone something. I'm sorry about that. Anyway, I'll go back and do that picture again. That's the y-intercept, 0, minus 5. We found a minimum over here, occurred at 1 over root 2. It's definitely below the minus 5. So whatever it is, it's certainly below it. I know it's negative. And we just went over here and we just figured out it was a negative number. So where's the x-axis over here? What does that tell me? There's only one real root. Let's figure out where it is, though. All right? So what I'm going to do is f of 0. And what's that going to be? Well, it's negative. It's less than 0. Oh, I was expecting that, wasn't I? F of 1. Right? What's that going to be? That's going to be 4 minus 6. That's definitely negative. No sign change there. F of 2. What does that give you? 32. Minus 12. Minus 5. And that's positive. So now I know there's a root. There's only one root, by the way, between the number 1 and 2. And I'm using the intermediate value theorem. I'm going to just show you the picture. We get there. And I go through Wells's work over here, and I'm seeing that root over here. All right? Let me point out over here, we said that was the y-intercept. We said this was the minimum. We said the minimum occurred at 1 over root 2. Sorry about that. Again, I'm not interested in the minimum, by the way, but we know what occurred there. When I mean minimum, it's relative minimum, certainly below the -5, all right? And we found the maximum over here. And that was a little bit more difficult because we want to know, was it negative or positive, but it turned out to be a negative number. All right, what does that mean below the x-axis? And we talked about that, and we got a root. How do we figure it's between 1 and 2? Intermediate value theorem, all right, between 1 and 2. Could you narrow it down to something better than that? Of course you could, all right, of course you could. All right, let's take a look. And again, I want to emphasize here, I certainly go through the technique he was doing in the notes, right? I certainly look through that, read that. It's a tough read, all right? So what we're going to do now is we're going to move forward. And I want to look at this. There's exercises, section 130, all right? Whoops. I do those, theorems. And again, if you want to do derivatives, let me see if I did that. Yeah, I did derivatives. And, I got pictures. What am I looking at? Possibly, simple stuff like y-intercepts. It's a cubic function, a maximum and a minimum, so forth and so on, all right? I can bound the roots, first root being between, when I say first positive root, between 0 and 1. And again, using intermediate theorem between -1 and 0. And then between 2 and -3, you'd find another root, all right? So I do this. It seems like he's doing cubics. He does a lot of that. Cubic. I say derivatives are really easy to analyze a cubic. I find this to be, I find it tedious to do, but I did it for you, all right? So you may want to look through that as well, all right? And I go through that, the derivatives with the root taking, all right? So again, over here, relative maximum there, y-intercept of 6, relative minimum here. I can look at this and know the root intermediate value between 1 and 2, and then 4 and 5, and I know a root between -1 and 0. Just look at the picture. And again, the picture doesn't need to be there. You can do the picture yourself, by the way. And again, getting a rough idea by using derivatives, all right? This one over here, I want to point out, you can blow these things up, and I hope you start to realize this is a much more difficult problem, all right? Now, why is that? It's not so clear, but I do know there's a maximum here. And if you did that, you would find out the maximum point, if you try to evaluate it, is a positive number, all right? You would know that looking at it, and you could even locate it. But again, I realize these things might be subtle, but you could do that, all right? You could do that, all right? So I go through that. Fourth degree polynomial, much more difficult, but I want to point out general shape of a fourth degree polynomial is going to look something like this. Now, what happens in the middle, I might not have a full understanding of it, but I'm going to say you could get 4 roots, you could have 2 roots, you get the idea. You could have no roots, and you could have 4 roots. You can have 4 roots, all right? So looking at it, what I do is I do some sign analysis, I do derivatives, and I kind of look at it, all right? I also want to point out I provide a good-looking picture for you over here. Again, you can blow these things up if you'd like. I can certainly find out these things over here. These are the relative mins maxes. You can figure that out. You could use the intermediate value theorem to find out where the roots are approximately. But it's a good idea to have a shape of it, all right? Now, what I mean by that, we're going into it with a shape sort of like this over here. And again, it's really not, you get a little bit more wavy than that, right? You get the idea. But yeah, it's a very crude technique, what we're doing over here. Very crude, all right? Number 6, fourth degree polynomial. Same amount of work. I do put the work down over there. I'm seeing the roots. You get the idea. How many roots to see? I'm seeing 4 roots. All right. I use derivatives to help me out with that. All right. Same thing for this one. Next one. I provide pictures for you for a good reason, by the way. We want you to look at those. I do that, the technique that he covers in this part of the text. You may want to look at that. All right. It's an important technique. And then I get to the SAGE code, right? What's SAGE? Computer Algebra System, or a CAS. It's open source software. Go to this website over here. You can either download the application or use the interactive web-based application. And my goal over here is just, take a look at it. What is this basically doing? Taking a polynomial, it's a fourth degree polynomial, and looking for the roots. And you can also graph this if you like. Here's the deal, though. What are we expecting to do? Look at the work. This is a tough section, though. And I'll make it even further tougher. What do? I start doing various techniques on it. I don't necessarily do his technique all the time. I show you various ways of doing the problem, answering the same question in a slightly different way. Does that mean you need to do that? No. You do what you're comfortable doing, all right? You do what you're comfortable doing. And I mean that. You do what you're comfortable. Here's the deal, though. You may be working these problems, all right? You may be working these problems, and you may decide that I made an error somewhere, whether it's numerical, conceptual, whatever. I don't care what the error is. Report it back to me. Tell me, you know what? I'm in section 130.3. Don't give me the page number. That's not helpful to me. Say I'm in 130.3. I'm doing problem number, 2, and I believe you made an error, and here's what I think the error is. What I'll do is I'll read your work, I'll look at my work, and I'll try to reconcile the two, all right? Do I make mistakes? I can't say sometimes. Of course I make mistakes. Is it helpful when people report mistakes to me? It is very helpful, and your name will go down in the book forever. It'll be there forever. It doesn't get removed unless you ask me to remove it. It'll go there. Now, you may report an error and say, please do not list my name. I won't list your name, but please be clear. If you're not clear, I'm going to list your name, all right? Thank you for paying attention.